Well, we are happy to welcome everyone in the 9th BioASQ workshop in the context of CLEF 2021. And we are also happy to have a very interesting program. This session begins with the overview of the 4 tasks that we supported this year. The 3 English, we may say, tasks on semantic indexing, question answering, and question answering for COVID-19, and of course the medical semantic indexing in Spanish. And then we have a series of presentations by the participating teams. In this session, we have mostly teams from the Task MESINESP and also a team from Task B. And later today, we have other presentations from Task B and Synergy mainly. Also, we are very happy to have an invited talk by Dina Demner-Fessman in the next session. And in the 3rd session, that will be also today, we will also be very happy to have a panel discussion on the explicit and implicit benefits from challenges such as BioASQ. And finally, tomorrow, we have the final and closing session with some presentations from participants as well. And of course, at the end of the workshop, we will have the announcement of the awards of the top performing, the winning teams for each task. So I don't know if Martin and Luis, as co-organizers, would like to have some words and welcome the attendance.
Well, yes, I like to. I want to welcome all the participants. Especially, I like to appreciate the effort of the people who is in other time zones, because these online events are pretty difficult to organize in terms of hours. So if you agree, we can start with your presentation, your overview, Tassos.
Sure. So I will share, I will open actually the presentation. Okay, so this is Anastasios Nentidis. Presenting the overview of the 9th edition of the BioASQ Challenge, actually with focus on the results of the tasks A, B, and Synergy. For those new to the challenge, BioASQ is a series of challenges on biomedical semantic indexing and question answering. And this year it is structured into 4 tasks. The 2 well-established tasks from the beginning of the challenge, Task A on semantic indexing and Task B on question answering. And the third task, we are happy to be the MESINESP Task on medical semantic indexing in Spanish that has been introduced last year, and it will be presented in detail in the next presentation. And finally, we are very happy to introduce this year the 4th task of BioASQ, the new task Synergy, where the aim is to use the BioASQ ecosystem to promote COVID-19 research. The participation in BioASQ in general can be partial in any task or subtask, and independent prizes are awarded to each task and subtask. This is the 9th version of BioASQ in the last 9 years. And in this diagram, we can see the participation of systems and teams in these 3 tasks of BioASQ. And we can see that the question answering tasks are attracting the most teams lately, while the semantic indexing task that has reached a really high performance of the top performing systems seems to have less teams participating. In task A, the task is formulated as a hierarchical text classification task, where the organizers distribute new and classified Medline articles, and the participants have 21 hours to assign MES terms to these articles representing their topics. Eventually, the evaluation of these submissions is based on annotations provided by Medline curators that are assigned manually in these articles. This task, as every year, is structured into 3 batches of 5 weekly test sets. In this slide, we can see the evolution of the training dataset from the beginning of the challenge of almost 11 million articles to more than 15.5 million articles this year, and as well as the expansion of the label set to more than 29,000 labels. In the table for the test dataset, we can see the distribution of articles into each test, and in the parentheses, we can see that most of these articles have been eventually manually annotated at the moment of evaluation. The evaluation measures employed for this task are a variety of evaluation measures for completeness, but the official ones are in bold. From the flat measures, it is the micro F measure, and from the hierarchical ones, it is the lowest common ancestor F measure, proposed by members of the BioASQ consortium. The results of the 9 years of this semantic indexing task reveals the continuous improvement of both the top performing system presented in red and the MTI, the baseline provided by NLM, presented in green. This last year, we didn't observe particular improvement, perhaps some small drop in the performance. I think this could be attributed to the concept drift towards COVID-19 related literature. In task B, focusing on information retrieval, question answering, and summarization, the organizers distribute new questions in English, in natural language, and the task is structured into 2 phases. In the first phase, the participants have 24 hours to provide relevant material, that is articles, snippets, concepts, and triples. And in the second phase, they receive from the organizers some relevant articles and snippets and have another 24 hours to provide answers, exact answers that are short phrases or entity names, and ideal answers that are paragraph-sized, query focused summaries. The evaluation in this task is done both automatically based on standard evaluation measures and manually by scores annotated manually to each response by the experts. This task is structured into 5 batches of bi-weekly tests. The training dataset in this task consists of more than 3,700 questions and have been developed by 13 biomedical experts and distributed into 4 question types. Questions that can be answered with a yes or no, factoid questions where the answer is a short phrase or an entity name, list questions where the answer is a list of entity names of unknown length, and summary questions where the answer is a paragraph-sized summary. The test data in this task consists of 500 questions distributed into 5 bi-weekly tests. The evaluation measures for this task are presented here. For phase A, for the information retrieval part, for articles, it is the mean average precision, the official one. For snippet, it is the F measure. For exact answers, the official measure depends on the question type. For yes, no, it is the macro averaged F measure. For factoid, it is the mean reciprocal rank, and for list, it is the mean F measure. For ideal answers, we rely on manual scores assigned to each response in terms of readability, recall, precision, and repetition by the experts that assess each response. The results on the information retrieval part for documents and snippets, though not really consistent through the years, we can still observe an improvement through the progress of the challenge. And in particular, in the last year, in BioASQ 9, we can see that the performance in both documents and snippets is more consistently high than in the previous year. In the exact answer generation part, Again, a lot of fluctuations are observed during the years, but still a trend towards improved results is observed. And in particular, in the last year, the results are better than and more consistent than in the previous year. Regarding ideal answers, we can see that the scores of the top performing systems are quite high, and in the last years above 4 in a scale of 5. And in particular, in the last year, they are quite more consistent compared to the previous year. In task synergy, we focus on open questions for developing problems, in particular on COVID-19. And the participants are required to provide relevant documents and snippets, as well as answers, both exact and ideal, where available. The task is structured as a continuous dialogue between experts and question answering systems that receive the feedback of the experts, which assess the responses of the systems in an iterative process. During this iterative process, the CORT-19 corpus, that is the resource for the documents, is also updated between each round. This task was organized into 2 versions of 4 bi-weekly rounds each. In particular, we had a team of 15 biomedical experts that posed in total almost 200 questions on COVID-19, and we had 17 teams participating with 45 systems responding with relevant material. The experts provided feedback and additional questions to these systems, which improved their answers and for the same questions, and this was repeated for 8 rounds organized into 2 versions. In this slide, we can see the distribution of questions in the 4 rounds of each version. We begin with 108 questions with no prior knowledge about them or relevant material, but the experts assess the responses of the systems and provide feedback to 101 of them, and also notify the systems that for 53 of them, enough material was found for providing an answer. This process was repeated 8 times. And actually, after the 4th time, a period of almost 2 months was left inside. And we organized the second version, where we kept some of the previous questions that were still open and relevant, and also added several new questions. In total, after all 8 rounds of the task, the systems managed to identify enough relevant material for answering 143 of these questions in total. And in particular, for 77 of these questions, they managed to provide at least one satisfactory golden ideal answer. The evaluation measures for this task are the same used for task B. However, for the retrieval part, we focus only on new material, that is, elements that are known to be relevant from the previous rounds are not considered. This seems to affect, of course, the performance in each round, as this seems to depend on the availability of new documents in each version of the resources of CORT-19, which in the second version was less documents than in the first version, where the COVID-19 literature was expanding more rapidly. In ideal answers, we can see that the top performing systems have quite high scores, and this suggests that experts may be quite satisfied even with early results from systems that are not necessarily perfect. In this map, we can see the worldwide distribution of the institutions of all the participating teams through these 9 years of BioASQ. And of course, we are grateful to all past collaborators, as well as to our platinum sponsor Google and silver sponsors PlanTL and Atticum. Thank you very much. And do you have any questions? Okay, if you don't have any questions, I think we can continue with the presentation of the MESINESP task.
Okay, I'm gonna share my screen, 1 second. Can you see my screen?
Yes.
Okay, perfect. So I'm going to start. Okay, good morning. I'm Luis Gasco. I'm a research engineer at the Barcelona Supercomputing Center. And in this talk, I'm going to present the overview of the results of the second edition of the Medical Semantic Indexing in Spanish task, also known as MESINESP, which is one of the tracks of BioASQ. This task is organized between the Barcelona Supercomputing Center and the Demócritos National Center of Scientific Research. First of all, I'd like to answer the question of why developing a semantic indexing task in Spanish. Well, Spanish is one of the most widely spoken languages in the world and is an official language in many countries. There are more than 150 million native speakers, and within the medical field, there are more than 180,000 practitioners only in Spain. For this reason, especially in recent years, we have noticed a large growth in the number of health documents written in this language. For example, as we can see in the image, we have experienced a strong increase in the number of scientific articles published in this language. This is especially pronounced in the field of medicine, in which the number of articles has doubled in the last 20 years. Something similar happened in other document types like patents, clinical trials, and electronic health records. This increase in information makes it more difficult to find relevant documents on specific topics. In fact, this fact makes the need to consult different sources, such as patent and clinical trial databases, which leads to the need to invest more time in searching for information. And time is very important, especially in times of health crisis scenarios like COVID-19 pandemic, in which the emergence of new virus required the rapid access of published information to act faster, developing vaccines, knowing new symptoms, etc. These information retrieval issues are partially solved with query expansion and semantic search techniques. We rely on data indexing, but data indexing has the problem of being a very complex manual process, which makes it an expensive, non-scalable, non-systematic, and very slow process, despite the existence of a large community of indexers that can make this manual indexation. That's why we organized the MESINESP task. The aim of MESINESP is to promote the development of semantic indexing system in Spanish to speed up the process either through pure automatic indexing or developing indexing support systems. MESINESP task has 3 subtracks, one for scientific literature, one for clinical trials, and one for patents. The systems are evaluated against a gold standard manually annotated by expert human indexer, and this task allows us to generate new resources such as gold standard and automatic generated silver standards, in addition to improve the state of the art of biomedical indexing in Spanish. As mentioned before, in contrast to the English task, the MESINESP evaluation set is manually indexed by the organizers, not by the organizer, but by 3 human indexers with expertise index. DEX codes are a multilingual hierarchical vocabulary written in Spanish, which contains more than 30,000 concepts to be used for indexing different types of documents, including scientific literature written in Spanish. These codes are revised every year. In our task, we asked the indexers to use the ACID indexing assistance tool developed by the Barcelona Supercomputing Center. And well, the interface is shown in the figure. And in this tool, the indexers could access the abstract of the document, read it carefully, and then incorporate the descriptors, the DEX codes, to each of the documents in an interactive way. For the generation of the corpus, we obtain a dataset of scientific articles from Biblioteca Virtual en Salud, a set of clinical trials from the Spanish Registry of Clinical Studies, and a subset of Google patents written in Spanish, After a filtering and selection process, a set of papers were annotated by the indexer, and these annotations were used as test set in the task. For the training and development set, we use previously generated resources. Just to mention that for the subtract 3, since DEX codes are not used for indexing this content, we propose the challenge as a domain adaptation 1, in which we provided a small development dataset and a subset of 120 patents for testing, which make this subtract more difficult than the other ones because of the lack of content. Here I show some statistics about the corpora. All the info can be consulted in the paper, but here you can see the average length of tokens for each document type, and also the diversity of unique DEX codes assigned to the documents, which show the difficulties of these tasks. We also provide additional data to the participants, such as medical entities detected in the documents using name identities recognition tools developed at the BSc. And well, this is everything about the MESINESP data. Let's go now on to the participation. This year, 35 teams were registered, 7 of them submitted results. The teams came from China, Switzerland, Portugal, Spain, Chile, and India. They developed a total of 65 different systems, and 4 of the teams decided to publish their results at this conference, and we'll see the presentation after mine. It is pretty noteworthy that 100% of them will participate in the task again, and large percentage of them, about 66%, are considering commercial exploitation of the results, which demonstrates the possibilities of this task and the interest of this task. The results of the task are shown in the table. For the second consecutive year, the Furano University team was the top performing team, followed by Roche, Pincotech, and Iria team, depending on the subtracts. In this slide, although only F-score results are shown, the Roche team obtained the best results in precision for the clinical trials and patent task. All the tables related to the results can be consulted in the paper. These F-scores may seem low, but the task is indeed pretty complex. On the one hand, the training data comes from different national libraries with different annotation quality management procedures, which makes that the data has some inconsistencies in the codes assigned to articles speaking about the same topic. Moreover, we use a rather strict evaluation measure, as we don't consider the hierarchical structure of the vocabulary when evaluating the prediction. For example, if an article had the code back pain, this code, and the system predicted only pain, it would consider it as incorrect when the system has somehow been able to capture part of the article content. Regarding the methods used by the participants, the top performing team used the BERT-based deep learning architecture with a multilingual BERT encoding layer, which was the vector space model used by most of the participants, followed by a multi-label attention layer. This team decided to pre-train the model using English language articles taken from Medline, from the other task. That was a very good idea to get the best result. We also did some analysis about the results. Given that indexing is critical in pandemic scenarios, one of the analyses performed was to check how the developed systems work with COVID-19 related documents. We found that the system had many difficulties in assigning the new DEX codes incorporated in 2021 related to COVID. This image shows how the system detects the first COVID terms defined in the 2020 edition on multiple occasions. However, they are not able to detect the new descriptors which are not present in the training set. That is, that the systems are not able to predict previously unseen label, so it would be interesting in the future to incorporate series of learning methodologies to at least try to learn them and improve the system to new type of data. In relation to the impact of the task, the state of the art of medical semantic indexing in Spanish has been improved by almost 6%, but there is still a great potential for improvement by looking at the evolution of its sister task in English. Despite the moderate performance results, we did some tests to see if the prediction systems would improve the manual indexing process time performance. In this text, where we use the ASIT tool and this prediction, the prediction codes generated by the participating system, we give this information to the annotators, and we show significant reduction in annotation times. On average, in fact, this reduction was in average 50% of the time among all indexers. We also, in the paper, propose the use of resonant similarity metrics at document level to consider the hierarchy in the performance metrics. Finally, just to sum up all the resources generated in MESINESP, we have had 13 teams, 14 papers, some gold standard and silver standard. The participants have produced 90 different systems to index semantic indexing system in Spanish. Some of the code is public, and trying to promote the semantic indexing tools, the Fudan and Bicomtech teams have developed 2 demos of automatic semantic indexing services, which are online. And we also developed the asset indexing tool just to be used for this task, and will be published soon. Encouraging knowledge transfer, we have published 8 videos in which participants briefly describe their architectures. And just taking advantage of this event, we would like to announce that there will be a 3rd edition of MESINESP next year, in which we will try to focus our efforts on integrating semantic indexing systems in electronic health records. Before finishing, we would like to thank all the people involved in this task, especially to the participating teams who, despite being a complex task, they always do their best to foster semantic indexing technologies. Thanks to CLEF organizers, BioASQ, especially to you, Tassos, and to our funding project that is the Plan TL in Spain. Obviously to the fantastic team led by Martin Krallinger at the PSC, the text mining unit, and all our colleagues in Pan American Health Organization and Instituto Salud Carlos III, and of course, the scientific committee. Here I show you the references to the paper in case you want to extend information that I briefly presented, as well as additional information about the task and the papers generated this year. If you have any question, please feel free to ask me, or we can continue and start the participant presentation. I'm looking the questions. Yes, we will have the 3rd edition of MESINESP the next year. It's approved. We will still working with DEX codes, but probably we are going to change it to apply it, or at least one of the tracks are going to be the semantic indexing of electronic health records, trying to improve or extend the semantic indexing to different types of documents. So I'm gonna stop sharing my screen, 1 second. And if you agree, we're going to start presenting the participating results. We are going to start with Huang, which is going to present their hybrid semantic indexing for biomedical article in Spanish. Huang, he's a doctor on computational biology, got it from the Chinese Academy of Science, and right now he's working as data scientist at the Pharma International Informatics Approach. He's based in Shanghai, and he's very curious about the future of healthcare in the light of data and analytics. So, Huang, the floor is you. Start when you want.
Thanks, Luis and Tassos. So it's great to meet you virtually. And can you see my screen now?
Yes, we can see your screen.
That's great. So hi everyone, this is Huang based in Shanghai. I'm a data scientist at Roche. So but everything today represents my own opinion. I'm going to present our participation on behalf of PIDNA team from Roche and Badajoz City University. I'd like to first thank the organizers for this fantastic challenge and workshop. So as introduced by Luis, The task contains 3 subtracks requiring semantic indexing with DEX terms in different scenarios. There are scientific literature, clinical trials, and patents. We basically attend all of them and rank this at the second team in the literature and patent subtracks. But today we would like to take the first track with the most training data set data as an example to demonstrate our system. So here is an introduction of our the task. So we know that the task is essentially a multi-label task classification task in natural language processing. And as the example show here, for each article, it requires to find the one or more labels with a control within a control label set. In this case, it's the DEX code. So there are several different kind of the challenge from the multi-label task classification. We know that there are flexible numbers of the labels per instance, and also there could be some speed issue if you're going to use a very huge model for different a lot of the candidate labels. And when there are a lot of labels distribution differently or unbalanced, it often biased to the high frequent labels. In the meantime, we know that for this task is in Spanish, so non-English context can be also a very interesting challenge in this task. Fortunately, we have different kind of solutions to resolve these issues. So we have the binary classifier sharing their same framework to tackle the first 2 issues. And then we apply a hybrid solution placing attention to the rare labels, which will be introduced later, especially for this kind of the bias to the high frequent labels issue. And thanks to the organizer, they actually provided valuable resources in Spanish. And we actually taking advantage of these kind of the valuable resources on data, vocabulary, and analytics. And actually, sorry. So we try to build our system on top of it. Here's the brief introduction of the dataset statistics. There are about 200,000 of articles in the training dataset, and as you can see that there are around 20,000 of labels for, in the candidate pool. So if we look into the distribution plot for each instance or articles, there could be 8 labels on average. But if you look on the other side, for each label, there could be different distribution of their supporting instance. It's quite long tail distributed, meaning that there are a lot of the labels with very few instances supporting their in the training data set. So to tackle this kind of the challenges, we use kind of the method to place some attention to rare labels. So first we will weight higher for those rare labels in the deep learning model for the BERT model, for example. I think this figure actually is very straightforward to demonstrate this kind of the idea. So for those labels with, if we try to balance this kind of the leverage, for those with the shorter arm, we need to place more weights there. And also for some entities, when the label is kind of entities, we can try to leverage the context information identified from the NER name entity recognition. Here is an example. We know that smoking increase risk for different kind of disease. Some of the disease entities are quite common labels, like the diabetes and the lung cancer, but some of them are not that frequent labels in our training data set. Or even some of kind of the entities are actually new in the test data set. So with the NER, if we can leverage this kind of information, of the context, we can easily identify this kind of entity and map them to our terminology systems, like the DEX code, so that we can identify them in few short or zero short way. Taking together, here's the overview of the our solutions of the hybrid semantic indexing. For frequent labels, we leverage the transformer-based multi-label task classification method, and for rare labels, we try to leverage the synonym matching on top of the NER. Of course, we can also check whether we can achieve some higher performance with this method. We also try to use this method as well. At the end, the two methodology will put together for their results, and we generate the final labels. In this slide, you'll see the implementation details for the BERT multi-label task classification. We leverage the Hugging Face package and also the BERTO pre-trained model. I think that's a very popular pre-trained model in Spanish in a BERT framework. And also the implementation details for the synonym matching. On the right, you can see that we show there's an example for the DEX synonyms. I think that's a very helpful and valuable resources. So we use the synonyms matching to the data in the NER results in the case insensitive way. And as previous that we achieved the second best team in the macro F1 scores, and to compare, we actually include one system purely based on the multi-label task classification of the BERT model, and to compare as the PIDNA 2, and our final system as the hybrid solution as the PIDNA. And from the result, we can see that it actually our hybrid system actually outperformed the pure solution of the BERT, indicating how we can like improve the BERT performance with very simple synonym matching. So we would like to thank the comments from the reviewers because they actually suggest us to compare our model versus the previous solutions, because we know that in last year there are some hybrid solutions as well, and our method actually performs similar to our outperforms their solutions with fewer base models, because as we showed, we only use 2 of them. And the improvement of the macro scores, if we look into the results here, basically the hybrid system improved a lot in the macro metrics than in the micro metrics, indicating that this kind of advantage of the NER-based synonym matching in the rare classes. And I think that's very important in the data sets with long tail distribution, especially for this kind of the synonym matching, for this semantic indexing scenario. And the model is quite efficient. So with only one GPU, the training step takes less than 1 hour. And for the final inference testing step, it actually only takes 5 minutes for the whole test. To conclude, we propose the integration of MLTC, NER, and terminology as a very promising approach for the non-English biomedical test mining. Of course, as indicated by Luis, that depends a lot of the resources, valuable resources on the non-English corpora. And this kind of the hybrid approaches can be also leveraged to other kind of the scenarios with this kind of corporal and the domain-specific knowledge. And in the future, if we will try to exploit the model and improve them, I think we can improve that in 2 ways. The first, that we can look into the NER step to leverage the DEX synonyms as well in the training of the NER model. And also for our training, we just use some arbitrary cutoff 3, which can be futurely improved for the hyperparameters. Okay, that's all. I think that's for our reference here. And I would like to thank you very much for the organizers again for this fantastic the challenge and the workshop. Muchas gracias, and we're happy to take questions if any.
Okay, thanks a lot, Keith. Does anyone has any question or something to ask to G about the solution? Well, I like to ask you one thing. Have you? Well, the test was pretty difficult. I mean, especially for the patent one, but do you know how your system works with different different length of the documents? For example, the clinical trials are very long documents, about 1,000 or 9,000 tokens, and the abstract only 300. Have you considered that for the different models?
Yeah, that's a good question. Thanks. So if we are leveraging the second part of the model with the synonym matching and the I think with the NER, I think that's not a big issue if the NER model can actually identify these kind of the entities. But for the first one, because we are leveraging the better framework, so I think only 500 tokens are allowed for the input. However, I think we can try to, for example, segment the input so that we can try to look in. Of course, there are also other kind of the models dealing with long content, like the Big BERT and other kind of the models. Yeah, that's kind of interesting because we didn't achieve a good result for the clinical trial subtract, but we are looking forward to play with that in the next year.
Yes, probably it's the most difficult track in my opinion, because of the length and the limitation of the models. But well, perfect. Thank you very much, Yi. Let's go to continue with the BICOMTech team. The presenter of the results is going to be Aitor García Pablos, who is a computer scientist and doctor in the field of sentiment analysis and opinion mining. He's currently working in the Human Speech and Language Technologies Department at BICOMTech Foundation, applying deep learning techniques to solve different problems in the area of natural language processing. So, Aitor, the floor is yours. If you want to start sharing your screen.
Yes.
Perfect.
Un moment, I can see this button here. Okay. So do you see the full screen now?
Yes.
Okay, so thank you very much. I am Aitor García Pablos. Well, I work at BICOMTech in the Natural Language Processing Group, and I am going to present our work, our participation at MESINESP 2 on behalf of my colleagues Nayara Perez and Montse Cuadros. So, well, let's go. This is more or less a summary. I'm going to briefly introduce the data and so on. It has been introduced already, so I will go fast. And then I will describe our systems. We have with two different flavors of system, let's say, but they are quite similar in their core, and then the rest of the details. So as we have said, MESINESP 2 is about semantic indexing of biomedical Spanish documents, and DEX codes are used as the output labels to let's say index or identify the documents. DEX is a hierarchical vocabulary and has a lot of different descriptors. Well, we will see that not all of them are present in the task, but several thousands are. So, and there are 3 subtracks, and we have participated in all of them. Basically, our approach is mostly supervised. So we have well, trained using the training data when available and trying to, well, basically, let's say bootstrapping from the previous training data and trying to adapt to for example, for the patents or the clinical trials using the development set or something like that with very small data for training. So as we can see here, the different data sets and the splits for training, development, and testing. As we have mentioned before, there is no training data for patents. The main task, let's say, is the one that has more training data. And the documents are, the documents contain different fields that can be used for training, like a title and abstract. There are other fields like such as date or journal, etc. But we haven't used them because honestly, we don't know if they could be of any use for this task. So basically, we have to stick to the title and abstract. And basically, that's it. About the DEX codes, it's something like this. Each code has an identifier, which belongs to a term. There are also different synonyms for each term, but we are not using the terms themselves. One of our systems will use the glosses, which are small short definitions like the ones there in the table. So again, to mention that there are thousands of terms. If I recall correctly, in the training data, there were about 22,000 different terms or something like that. But the distribution was very imbalanced. As it has been said before by the other participant, some terms are of very high frequency. They appear in almost every document, and some others appear only 5 times in all the more than 200,000 documents. So it's very difficult for a supervised model to learn to label such terms. It cannot see them, but only once or twice in the whole training set. So that's it. As I have said, we have participated with 2 different transformer-based architectures. In fact, they are BERT-based, but what we want is to encode the documents using a transformer model. It could be BERT or other flavor of transformer architecture. So what we do in both of the systems is to use BERT to encode the input text-based information and project that encoding, doing some things in the middle, but projecting those encodings to a level space, the DEX codes, which can be of several thousand. We have tried to put off pruning the long tail of very infrequent labels to just to the systems can work with all the levels at the same time, but it's a waste of resources because again, with only 2, 5, or 10 occurrences in the whole training set, the model will not learn to label them. And basically that's it. We have given different names to distinguish the both systems. CSS, because we use the CLS special tokens from BERT, and the other is label glosses because it's kind of similar, but we inject information from the glosses from the DEX codes, trying to improve the model. So that's it. This is the CSS model. Basically, as I have said, what we do is to input the text, the text content we have for each document, which is the title and the abstract, and we encode as in the image using the typical BERT encoding, CLS special token first, then the title, then a separator token, and then the abstract and a trailing separator token. The whole abstract fits in BERT with the BERT gen, except for some rare documents. We calculated that the average length was about, I don't remember exactly, but 280 BERT tokens or something like that, with a standard deviation of 30 or something like that. So with 300 tokens of maximum length, you can fit almost every document in the training set. And well, with this encoding, what we do is to pick those special tokens as beacons or flags, let's call them, to concatenate them, and those will be the representation for the whole document in order to go to a multi-level classifier layer. That's basically that. There's not much mystery in it. We could have done different things in order to represent the document. The rationale here is that, for example, the typical thing that is done with BERT is to use only the CLS token as the classification head or something like that. But we thought that it was too much information in a vector of 768 positions, was to condense too much information in order to predict, let's say, 10,000 different labels. So we wanted to have a larger document representation to be able to represent so many labels. And the other model is quite similar, but has some differences. What we do is to pick all the label glosses that are in the DEX, in the DEX definition, the whole hierarchy of terms. And what we do is offline, we encode all of them using the same BERT or transformer model we are going to use during the training. And with this simple paradigm, we just obtain the, let's say, the average or one embedding per the whole clause of each label. So those embeddings per each clause go to an embedding layer within the model, and when we are training, we again encode each document. In this case, we are not using the CLS subset. What we are doing is the same that we have done with the glosses, averaging the whole document, and then we concatenate per each possible label gloss and the document. We create, let's say, an extended embedding, and that goes to a classification head. So for we obtain. If we have C different labels, we obtain C pairs of document label, embeddings, and that will predict 1 or 0 depending on if that code applies to the document or not. And more or less that's it. It's a reformulation of the previous model, only that injecting the information from the classes. The rationale here, what we wanted here, is that the fact that such a supervised model cannot ever predict a code, a label that hasn't been seen in the training data, or if its frequency is very low, the model will never be able to predict that because it's just relying on the training examples. And we wanted a way of saying, okay, this is the meaning or the semantics of the codes. Maybe even if you haven't seen it very often, you can, with this semantics injected, you can come up with a way to predict that code if you see a document that really fits. I don't think this is the case because the other model works a bit better, but well, that was the idea. So as we have said, they are multi-label classifiers, not much mystery here, only that each possible output, each possible prediction is a continuous value between 0 and 1. Because, well, for each label, the model outputs the confidence on if it's about to predict that label or not. So a threshold must be set that there to be more permissive or not, to improve the, let's say, the precision of the recall of the model. So we have adopted a global threshold for all the labels. It could be fine-tuning for different labels depending on if they are more or less frequent, if the model is more prone to predict one label or not. But we did some quick experiments and we didn't get better results. So basically we have set a global threshold, making some experimentation with the development set. Well, of course, a threshold of 1 would mean that no code is ever predicted, and a threshold of 0 is that whatever score you get, just say that you predict this code. So there is a trade-off of the sensitivity and specificity of the model, depending on how you vary this threshold. And after the experimentation we have done, well, the optimal threshold was in the range, as I said, 0.25, 0.30. It sort of makes sense because there are a lot of codes that are much less frequent, so the model is less confident about emitting them. So instead of the, let's say, the default 0.5 threshold that you would set blindly, it's reasonable that the threshold is a bit lower than that. And for the training setup, we have used ISAMBERT instead of BETO. I think we also did some experimentation with BETO. ISAMBERT is a BERT model pre-trained by the Asia group at the Basque Country University. Basically, it's a BERT model pre-trained with data in English, Spanish, and Basque. So, well, that multilingual capabilities maybe boost a bit its performance. We have tried with ISAMBERT, basically. And our training hardware was an NVIDIA 2080 Ti GPU, so we don't have very large GPUs to do that. The average training took about 3 to 4 days. Maybe you need to leave it almost a week in order to see if the training progresses more, but our experience is that there was a ceiling there that was reached even before the time lapse. For all the models, all the experiments, there was always a ceiling that we thought that is what the training data assists with no hybrid approach or extra information from outside is the as far as the model can get with that data and then projecting it to the development set. So basically in that time, we reached the maximum for all the models. And well, the other things there is the hyperparameters. The one to be remarked is the cutoff of 80 is the number, the minimum frequency allowed for a level to be cut off. We have tested different cutoffs. So basically, there are more than 200,000 documents in the training data. So if a label appears less than 80 times in the whole data set, it's very rare, and we were cutting them. We did that using a little heuristic. We wanted to minimize as much as possible the label space in the training data, but not maximizing as much as possible the label space in the development set. So not capping the capability of the model to predict labels that are in the development set, so are labels that we are interested on. And that's the number we got. With that number, the output space of the label space was about, if I remember correctly, 4,000, 5,000 of labels instead of the 22,000 that will be if we add all the labels that were there. So these are the results, more or less, with the different runs we submitted. The small numbers next to the name of the run are the threshold we have tested to submit the different runs. The CSS model, also the label closest model using IS and BERT, as we have said. And well, the results are quite similar for all the runs. We are way behind the leader, the winner system in the competition, but still is quite reasonable result. It's true that, as I have said, I think there was some sort of sailing there with the training data and the supervised approach we were using. So a hybrid system or some way to inject extra information from other data sets, or maybe pre-training, or I mean, more information inputs is necessary to make a model learn beyond certain sailing that it has there. And well, for the other subtracks, what we did is to, in particular for the ones that didn't have training data, what we did is to pick the checkpoint training in the subtract one, and then train further with the little data we had for those subtracts. So yeah, just to make the model not to start from scratch, because at least the model already knows what the DEX codes are, or has some notion of what the task is, and then we fine-tune a bit more using the subtractors training data, or even a small set of the subtract rest development data in order to try to improve the model a bit. And well, those are the results. We are still behind the winning systems. So as the conclusions, well, we have submitted 2 different transformer-based models. Worth mentioning that they are quite fast also. Those models can process about 80 documents per second using a commodity GPU. It doesn't require a very large or powerful GPU, just a common one that has 2, 3, 4 gigabytes of memory. And well, they are fast, they are easy to use and lightweight. And despite the huge level space, which have many thousand, and they are very unbalanced, the models achieve, let's say, promising results. I mean, of course, they need more, as I have said, more information input or a lot of more work and experimentation to improve it, because we are still far behind the winner system. But even the winner system doesn't achieve an F score of 0.5, so it means that the task remains challenging and it's very interesting. So it's not solved. So we are willing to participate in further competitions, and basically that's it from my side. If there is any question. You are muted, Luis. Sorry.
Okay, Aitor, thank you very much for your presentation and your effort. I think you have some questions in the chat, but we are having some time schedule problems. So if you don't, you can answer the question on the chat, and let's start with the next presenter, if you don't mind.
Okay, I will answer in the chat, and we can.
Okay. Thank you very much, and sorry for this, Aitor.
No problem at all. Thank you.
So let's continue with the Cole and Liz team. The presenter is going to be Francisco Ribadas-Pena, who is an associate professor at the Computer Science Department of the University of Vigo. His main research topics are information retrieval, NLP in Spanish and Galician, and machine learning in general. So, Francisco, you're going to start when you want. Thank you to be here and to participate in our task.
Thank you. Well, my name is Fran Ribadas. I am a member of the Compiler and Languages Research Groups from the University of Vigo. And this is a joint work between the Cole group and the Liz group from the University of A Coruña. This was our second participation on the BioASQ MESINESP Spanish task. Our approach, both in the English and in the Hispanic semantic indexing task, follows a very simple similarity-based strategy. We propose a flat categorization without using hierarchical information, using a large k-nearest neighbor multi-label classifier. Our goals in this participation were to test the suitability of large KNN categorization for Spanish, evaluate different article representations, and test the performance of sparse versus dense representations in this kind of categorizations. As I said before, our approach applies a similarity-based subject assignment. In our participation, we have evaluated two sources of similarity: the matching scores computed from the sparse index terms stored in an Apache Lucene index, and the Euclidean distance computed between dense document level vectors. Our classification procedures starts creating an indexable representation of the articles, which is queried to identify similar articles. The DEX codes assigned to those similar articles are employed both to predict the number of DEX codes and to rank the topmost codes assigned to a given text document. Regarding the sparse representation approach, we have evaluated several index term extraction methods, both using linguistically motivated and statistically motivated approaches. We have considered single word terms with statement-based representation and a morphosyntactic based representations created using the part of speech tagger from Spacey toolkit. We have also included several approaches for extracting multi-word index terms. We have employed known phrase chunks identified by Spacey, triples of syntactic dependencies using the Spacey dependence parser for Spanish, and statistically motivated candidate keywords extracted by the test rank algorithm. We have also employed the named entities provided by the MESINESP challenge organizers. And finally, we have also indexed the list of exact matches of DEX labels found by the UIMA concept tagger. Here we show an example of the kind of index terms we have extracted for one of the training documents, and the kind of single and multi-word terms. We have also evaluated a complementary index term matching approach that replaces the Lucene index matching. We have associated to each index term in the trained dataset a list of these codes which have a high correlational level with each index term. The intuition behind this experiment is that the presence of this kind of terms could be a good predictor of the convenience of labeling a test document with a related test code. We have employed the normalized pointwise mutual information as the co-occurrence metric, and we created a sort of inverted text code profile using lemmas as single word terms and nominal phrases, named entities, and keywords as multi-word terms. In our experiments, the actual behavior of this method was equivalent to performing an exact match with this kind of pseudo-synonyms that our method discovered. Here we have an example of these inverted text codes profiles. Surprisingly, this method obtaining fairly good results in subtask 3, sorry. Maybe because this behavior of exact matching and finding pseudo-synonyms. Well, here we have an example of the term and the related codes with the mutual information scores for each pair. And this is a set of profiles related with COVID-19. Regarding the dense representation similarity, we have also followed a very simple approach. Our dense representations vector were created using sentence level embeddings. We convert the natural language sentences into dense vectors with enriched semantic using pre-trained models from the Semantic Transformers project. The indexing procedure was as follows. We split the trained articles into paragraph and sentences. We compute the sentence level dense vectors using the sentence transformer models, and the final document level dense vector is the average of these sentence level vectors. Finally, we store those document level vectors into a phase index. The labeling of a test articles, we create its document level dense vector and query the phase index to retrieve the top k closest vectors according to the Euclidean distance. And these similar articles are employed to predict the ranked list of candidate text codes. We have evaluated 2 sentence transformer models without fine-tuning. We have employed a pre-trained multilingual sentence level model and a pre-trained monolingual word level model. In our preliminary experiments and also in the official runs, the performance of this method was below the sparse representation similarity method I have explained before. And this is a review of the official runs we have submitted to the challenge. The system area 1 follow the sparse similarity using all of the index term extraction methods with using 20 neighbors. Area 3 followed the dense similarity using 40 neighbors. Area 4 employed the inverse text code profiles using the first run, Area 1, as a reference. Area Mix created the list of candidate text codes mixing the predictions from Area 1 and Area 3 and added the exact matches retrieved with the UIMA concept mapper. We have also employed in the subtask number 3 the area system. We employed a mix of the inverse text code profiles and the exact matches created by concept mapper. This is the results. Our systems were far from the top competitive systems. we obtaining fairly poor results with the dense vector representations. In our preliminary experiments on the development dataset, our results with dense representations were fairly better. We think that the reason of the poor results with dense representations may be due to the lack of fine tuning in the embedding models. We have also participated in the English subtask in the BioASQ task 9A, and we submitted results from a system similar to IRIA1, but using only steams and selected bigrams. The results were fairly better in English than in Spanish. And finally, as next line of work, we plan to improve the dense similarity with fine tuning the models and using more sophisticated methods to compute the document level vectors. We also want to test the dense similarity approach in the English subtask, and we plan to find ways to exploit the hierarchical information and the co-occurrence information in order to improve the prediction. And that's all. Thank you very much for your attention. If you have any questions.
Okay, Francisco, thank you very much for your presentation. I think that your system was somehow robust to new labels, and I didn't say anything about this, but your team was the only one who were able to predict some of the codes not seen before. So somehow, despite not having the best F-score, you have very interesting modules inside your models that can be of interest for the community. So thank you for sharing your results. Has anyone some question, or? Well, if you have any questions, you can write it on the chat, and I think that Francisco can answer there. And well, to continue, to continue with the last MESINESP participant who decided to share the presentation here at CLEF. It's Pedro Ruas from LASIGE-BioTM. Pedro, he's a master's degree in bioinformatics, and he's currently a PhD student in the LASIGE group. He has been working with name identity recognition and linked models with a focus on biomedical entities. And well, Pedro, the floor is yours. Thank you for your participation. We are willing to listen your talk.
Okay, thank you, Luis, and the organizers for the opportunity for being here today. Let me just share my screen. Okay. Can you see my slides?
Yes.
Okay. So my name is Pedro Ruas, and I'm here at behalf of the LASIGE-BioTM team. I'm going to present our approach to the MESINESP 2 track, and the title of our article is Entity Linking with Semantic Similarity and Extreme Multi-Level Classification on Spanish Biomedical Documents. So our team participated in the 3 subtracks of MESINESP 2, more concretely on the scientific literature subtrack, on the clinical trials subtrack, and on patents subtrack. And we considered each of these subtracks as a distinct extreme multi-level classification task. In this task, we have a very large collection of documents that we want to classify. We have a very large label list, which in this case corresponded to the codes of the DEX vocabulary, which included more than 34,000 labels or codes. And then the goal of this task was to develop an automatic approach to automatically assign each document with the most relevant labels. And our system included two different components, the entity linking one and also the classification module. And our guiding hypothesis was that if we fed only the most relevant entities identified in the documents to the classification algorithm, this could lead to an increase in the performance in the classification task. Beginning with the entity linking module, we have used the additional data provided by the organization, and this data contain the recognized entities in the documents of the three corpora. We have here an example. We have 4 recognized entities and the respective spans. And then we applied the entity linking model, which consisted of the PPR-SSM tool, which is a tool that was developed by elements of our group based on personalized page rank algorithm and semantic similarity. And we have used this tool to link the recognized entities to the respective DEX codes. As we can see here, we have the same entities, but in the output of this stage was the association with the DEX codes. At last, we have developed a semantic similarity filter. We have used the Resnick's measure in order to calculate the semantic similarity between pairs of entities included in a given document. And the score of the entities was equal to the averages of the semantics of the values for the semantic similarities between the other entities. And then we have 2 different filters. In the first case, we have the top 25% filter, which means that we only fed the classification algorithm with the top 25 relevant entities I identified in the document. And we also had the control scenario where we fed the classification algorithm with all the identified entities in the document. So the classification model was based on the X-transformer algorithm, and this includes 4 different steps. In the first step, the preprocessing, the titles of each document, the titles of the documents are stemmed and then concatenated with the DEX codes associated with the entities previously identified. Then we have the semantic label indexer, which basically generates representations for the labels or the codes, and then cluster them in order to reduce the space of possible labels. Then the deep neural matcher basically fine-tunes BERT in order to map each text instance or document to a set of relevant clusters. And then at last, the ranker models the relevance between each text instance and the labels belonging to the limited set of clusters. And for the key parameter, which defines the number of labels associated with each document, we have only explored the value 20, which means that each document was always associated with the top 20 labels. We have followed different training approaches. For instance, for the scientific literature subtrack, we had 2 different models, LASIGE-BioTM 1 and 2. And the difference between them was that we used a different value for the semantic similarity filter. In the first model, we fed the classification model with all the identified entities, but in the second model, only the top 25 entities were fed. And the deep neural matcher, in this case, in these 2 models, consisted of a model that was previously used in the first edition of MESINESP. Our team basically fine-tuned the BERT multilingual based case in the training files of the first edition of MESINESP, and then further fine-tuned on the training files of the Cantemist competition, and at last this resulting model was fine-tuned on the training files for this subtrack. For the clinical trial subtrack, the setup was similar, but we have used a different model for the deep neural matcher. We only fine-tuned the BERT multilingual in the training files of the scientific literature. For the patents subtrack, we only had one model, which was BERT multilingual based case. So in terms of results, we can see here in this table that they were low compared with the best results highlighted here, but also compared with the baseline results. And with respect to the initial hypothesis that we wanted to validate, for example, for the first subtrack, we can see that the application of the semantic similarity filter did not work, because the second model, the one that was only fed with the top 25% entities, obtain lower performance compared with the first model. However, for the second subtrack, the opposite happened. So we cannot validate the initial hypothesis that feeding only the most relevant entities leads to an improvement in the classification task. These low results are probably explained by the fact that we were only able to train each model during a single epoch, since we had very little time available to train the models. So one way to improve these results would be the hyperparameter optimization, with particular focus on the number of training epochs. And besides, for the clinical trials subtrack, we decided to use the training files of the first subtrack, but probably it was not the best decision because we would obtain maybe a better performance if we have used the training files for this subtrack. And since we had problems with the availability of time, we also could explore, for example, lighter versions of BERT, like the Spanish version of DistillBERT, in order to reduce the training time associated with the models. And besides, we only fed the classification algorithm with the stem titles of the documents. And we did not explore, for example, feeding the abstracts or feeding other parts of the documents. So in the future, maybe a possible approach is to apply, for example, an automatic summarization tool to summarize the abstracts and then feed the classification algorithm. And at last, we only have used the value 20 for the key parameter, but if we look at the documents of the first subtrack, the scientific articles, on average, each document was associated with with 10 labels. So probably different values for this parameter would obtain different performances. So thank you for listening. If you have any questions, feel free to ask.
Okay, thank you, Pedro, for your work. I have a question, and it's about the resonance similarity measure. Did you find any problem to apply this measure? Because we know that we have that in the text ontology there are some cycles that can make or can provoke difficulties in applying this measure, or you directly apply this measure in the mesh ontology that it's pretty similar in the structure to DEX.
Yes, it's true that the DEX vocabulary, I think it's an acyclic graph, so that raises some problems. But in this case, we have just considered the vocabulary as a direct graph. So we have just applied this measure, and we have not checked if effectively these results made sense, since we had a limited time. But it would be an interesting thing to further analyze in the future. Yes, for example, if you try with other ontologies or vocabularies, if these results would be different.
Okay, perfect. Very interesting, Pedro. We are going to continue. I think that Martin has written a comment to all of the participants of MESINESP to keep in touch, speak with you in the future about semantic classes in the DEX hierarchy. But well, we are going to continue with Tiago Almeida. This is not a participant of MESINESP, but a participant of the BioASQ Task 9B. So Tiago, the floor is yours. Thank you very much for presenting your results, and you can start wherever you want.
Okay, hello. Are you seeing my screen?
Yes, we can see.
Okay. So hello to everyone. My name is Tiago Almeida, and I'm a PhD candidate at University of Aveiro, Portugal. And today I'm going to present our participation in this year's BioASQ challenge entitled Universal Passage Weighting Mechanism in BioASQ. This is the outline of this presentation and is the following. First, we start with the motivation, followed by an introduction of our architecture. After that, the pipeline and the training methodology will be addressed, followed by a brief description of the runs submitted to this year's challenge. And that at the end, we show the results and discuss the results as well as some conclusions and future work. Information overload in the academic context has become a trending topic where researchers are overwhelmed with the current rate that new research is published. However, thanks to international challenges like BioASQ, each year new automatic searching systems are presented as possible solutions to aid these researchers. Following our last year participation, we have been working in the new specification of our neural model that tries to combine the human way of searching information with the current advance in the deep learning. We call it Universal Passage Weighting Mechanism, or UPWM for short. Given our previous motivations, we decided to use it to participate in this year's BioASQ challenge, more specific in the ad hoc retrieval task. Since our mechanism tries to mimic the way that humans search for information, let us first summarize this almost unconscious behavior. So when we search, normally we first look for a specific region of interest within the document, mainly denoted by some specific term related to the information need. Then we read the associated text in the specific region and assign a mental score of relevance. Finally, we aggregate all the relevance gained and conclude if the document was relevant or not. As previously presented, the human methodology of searching gives us the tool to quickly find supported answers without the need of reading the entire document. In other words, we managed to derive a notion of relevance by simply looking at some sentence from the document. The UPWM, by approximating this mechanism through neural networks, is also able to derive a similar notion of relevance for documents by only considering a subset of its sentences. Therefore, this can be viewed as a sentence-level aggregation mechanism. But what is this mechanism and what problems tries to solve? And in short, it's a mechanism that enables deep learning models to derive a judgment over longer documents, since usually documents are larger and cannot be directly fed to the models. In the image below, we represent the struggle that the standard state-of-the-art model BERT has when analyzing a long document, since it is too big to fit in its input shape. Even if we built a wider transformer model, it always would have the quadratic complexity issue of the self-attention layer. So feeding the entire document just becomes unfeasible. An alternative to this is to consider the document as a sequence of sentences that the model processes in parallel. Then the document relevance should be some sort of combination of their individual sentence scores. This is usually an overlooked problem in the literature, and as far as I know, only simple techniques were tested, like selecting the max sentence score or doing some average or on other types of combinations. So in here, we present an overview of the current architecture, which has 3 steps: the sentence splitting, the sentence relevance block, and the document sentence block. The first part is just responsible for the splitting of the document into a set of passages that define our regions of interest. Next is the sentence relevance block. It has the objective of individually approximate the notion of relevance for each document sentence, similarly to how humans do it. It is divided into 2 parallel layers: the a priori layer, which implements the human heuristic of finding the information by only considering the regions of interest, and the interaction model, which implements a neural model that mimics the careful process of reading and analyzing the relevance of each sentence. Looking with more detail to the a priori layer, the main idea is to produce sentence scores without thoroughly processing the sentence. Therefore, its name, since you are giving a priori kind of score, before analyzing the sentence. To accomplish this, we first find regions of interest by looking at exact or close to exact matches occurrence in the interaction matrix. Then we select the most important matches by filtering with a specific threshold. And at last, we collapse the passage dimension to get the terms that appear in that sentence. Now, if you run this layer in the full interaction matrix with a threshold of 0.7, we get that this sentence contains the first and the last term of the query, and therefore becoming a region of interest for our model to analyze. Note that the first term that we found only has a similarity of 0.85. However, it was included since it was higher than our chosen threshold. This means that by controlling the threshold, we can define how much we want the semantic similar terms to be included as a region of interest. We further weight the resulting query terms that appear in a sentence by considering their individual importance, that appear in the query. For that, we use the embedding representation of each query term combined with a trainable weight in order to compute their importance. Finally, the a priori layer score is given by the weighted sum of the query terms presented in each sentence. Note that these scores came from the a priori layer are bound between 0 and 1. So this entire layer can be seen as a filter or a gate that selects the sentence that will contribute to the final document score. The interaction model just acts as a placeholder for more complex models that can derive relevance scores for query passage pairs. The final sentence score is computed by combining the a priori layer score with this score from the interaction model. And once again, the a priori layer in here will mimic the human, trying to decide what sentence the interaction model should consider or not. Finally, the last block just aims to produce the final document score based on the passage scores previously obtained. To avoid creating bias for longer documents, since they have more sentences, we employ a feature selection step. Then the document score is computed by feeding this vector to a multi-layer perceptron. We decide to create two concrete implementations of the UPWM model for the BioASQ challenge. More precisely, here we describe the two types of interaction models that we use. The first one we called Lightning UPWM, that is extremely lightweight and only requires the CPU to run. And another version is the Transformer UPWM that uses the frozen PubMed BERT model, which achieves stronger results but requires specialized hardware to run. Since the BioASQ used a large collection, we adopted a traditional two-stage retrieval pipeline with the BM25 for the first stage. For training, we used the pairwise cross-entropy loss and made experiment with joint training by combining the document loss with pointwise and pairwise snippet loss. All the experiments were implemented in TensorFlow. In the first three batches, we only submitted runs with a pairwise loss for the documents, and RRF stands for rank reciprocal fusion and is an ensemble technique. Then on the fourth, we added the joint train with a pointwise loss for the snippets, and on the fifth, with the pairwise loss for the snippets. First, we present the results of our runs that we submitted. In blue are the Lightning version and in green are the Transformer versions. The Transformer version considerably outperformed the Lightning versions by a difference of roughly 3 to 4 percentage points, which correspond to 10 to 12% improvement. When comparing with the baseline, we witnessed that narrow re-ranking almost always managed to improve the BM25 ranking order, and only the Lightning version in the last batch failed to outperform the baseline. When comparing to the other competitors, we compare in here our top run, and that was the Transformer version, against the median scores, and we managed to consistently stay above it. And then we compare our top submission with our top competitor, and we managed to achieve the top position in 3 of the 5 batches. Note that all of these results are from the paper and correspond to the first phase of evaluation. Then on the second phase of evaluation, our model lost competitiveness when compared to the top competitor. However, when compared to the second best, that is on the right side, the difference became marginal. At last, we arrive at the snippet evaluation, and very briefly, we achieve higher scores on the first phase of the evaluation. when using the pairwise snippet lost, and similarly to the document task, it lost competitives in the second phase. In this work, we show a synthesis level aggregation mechanism that is inspiring the way that humans look for information in large documents. We show two simple configurations, the lightning and the transformer version. We achieve highly competitive results in the first phase of the evaluation. Despite being less competitive on the second phase, we still managed to score close to top positions. And for future work, we aim to continue evolving this mechanism, while also testing a strong configuration of the transformer version, recalling that we used the PubMed BERT, however, we did not train it, neither fine-tuning it. So I'll conclude my presentation, and if you have any questions, feel free.
So thank you, Thiago. I don't know if someone have questions in the chat. I don't know if Tassos want to do some kind of comment about the work. I think it's pretty interesting.
Yes, thank you very much, Thiago, as well as all the participants. I have noticed that the performance of your system, as well as for other systems, is highly related to the metric that is used, of course. But I found interesting that the position of your system was quite different in the mean average precision, that is the official measure for documents, which considers the order of the documents, compared to the F1 measure for the documents, which doesn't consider the order. Do you think that could be available some way or some idea of how to incorporate order information in the fine-tuning of your approach, so that it could be more tailored for ordering the results that you already achieve with high precision?
Well, I think the F1 metric for document ranking is not like a very well-designed metric in terms of, because it doesn't capture order, and I'm interested in capture order. And F1 can be also like a bit, I don't say exploited, but for instance, we can retrieve at most 10 documents. And in the map, I can always retrieve 10 documents, and I will not be injured. While in the F-score, for me, I can achieve high precisions if I retrieve less than 10 documents. So I can maybe, if I want more precision, I can build a module that instead of giving me a ranking order, gives me a relevance value of 1 or 0. And then I can select a threshold. And that way I will achieve a higher precision. But then that will cost me recall. And well, it's a balanced game. So since the map is the official metric, I didn't even consider F1 score in my experiments.
I see. Thank you. This is very interesting. So the fact that we have a frozen length for each response affects the evaluation of the system, because in each case, perhaps it's different, the actual length of relevant items. So retrieving always 10 elements, it's kind of more difficult for the systems. Thank you very much, Thiago.
Thank you.
So, well, thank you. I think that the first part of the session is over. Am I right, Tassos?
Yes,
we
yes.
have a 1 hour break, and then we will have the conference paper, the best of labs. So
yes,
we will see us again at 15:30 in Bucharest time.
Yes, and then we have our BioASQ session again at 15:30 Bucharest time with 2 presentations from Task B, and of course the invited talk with the Andrade and Francisco M. Looking forward to see you there.
Yes. So thank you very much for coming here, and see you again in an hour, in 2 hours more or less. Thank you.
Thank you all.
Thank you.